Longitude is a geographic coordinate that specifies the east-west position of a point on the Earth's surface. It is an angular measurement, usually expressed in degrees and denoted by the Greek letter lambda. Points with the same longitude lie in lines running from the North Pole to the South Pole. By convention, one of these, the Prime Meridian, which passes through the Royal Observatory, Greenwich, England, was intended to establish the position of 0 degrees longitude. The longitude of other places was to be measured as the angle east or west from the Prime Meridian, ranging from 0 degree at the Prime Meridian to plus 180 degree eastward and to 180 degree westward. Specifically, it is the angle between a plane containing the Prime Meridian and a plane containing the North Pole, South Pole and the location in question. Pointing from the Earth's center toward the North Pole and the x-axis extending from Earth's center through the equator at the Prime Meridian. A location's north-south position along a meridian is given by its latitude, which is the angle between the local vertical and the plane of the equator. If the Earth were perfectly spherical and homogeneous, then longitude at a point would just be the angle between a vertical north-south plane through that point and the plane of the Greenwich meridian. Everywhere on Earth the vertical north-south plane would contain the Earth's axis. But the Earth is not homogeneous, and has mountains Seguro, which have gravity and so can shift the vertical plane away from the Earth's axis. The vertical north-south plane still intersects the plane of the Greenwich meridian at some angle. That angle is astronomical longitude, the longitude you calculate from star observations. The longitude shown on maps and GPS devices is the angle between the Greenwich plane and not quite vertical plane through the point. The not quite vertical plane is perpendicular to the surface of the spheroid chosen to approximate the Earth's sea level surface, rather than perpendicular to the sea level surface itself. History. The measurement of longitude is important both to cartography and for ocean navigation. Mariners and explorers for most of history struggled to determine longitude. Finding a method of determining longitude took centuries, resulting in the history of longitude recording the effort of some of the greatest scientific minds. Latitude was calculated by observing with quadrant or astrolabe the altitude of the Sun or of charted stars above the horizon, but longitude is harder. Amerigo Vespucci was perhaps the first European to proffer a solution, after devoting a great deal of time and energy studying the problem during his sojourns in the New World. As to longitude, I declare that I found so much difficulty in determining it that I was put to great pains to ascertain the east-west distance I had covered. The final result of my labors was that I found nothing better to do than to watch for and take observations at night of the conjunction of one planet with another, and especially of the conjunction of the Moon with the other planets, because the Moon is swifter in her course than any other planet. I compared my observations with an almanac. After I had made experiments many nights, one night, the 23rd of August 1499, there was a conjunction of the Moon with Mars, which according to the almanac was to occur at midnight or a half-hour before. I found that at midnight Mars's position was 3.5 degrees to the east. By comparing the positions of the Moon and Mars with their anticipated positions, Vespucci was able to crudely deduce his longitude. But this method had several limitations. First, it required the occurrence of a specific astronomical event, and the observer needed to anticipate this event via an astronomical almanac. One needed also to know the precise time, which was difficult to ascertain in foreign lands. Finally, it required a stable viewing platform, rendering the technique useless on the rolling deck of a ship at sea. See lunar distance. In 1612 Galileo Galilei proposed that with sufficiently accurate knowledge of the orbits of the moons of Jupiter one could use their positions as a universal clock and this would make possible the determination of longitude, but the method he devised was impracticable for navigators on ships. In the early 18th century there were several maritime disasters attributable to serious errors in reckoning position at sea, such as the loss of 4 ships of the fleet of Sir Cloudesley Chauvel in the Scilly naval disaster of 1707. Motivated by these disasters, in 1714 the British government established the Board of Longitude. Prizes were to be awarded to the first person to demonstrate a practical method for determining the longitude of a ship at sea. These prizes motivated many to search for a solution. John Harrison, a self-educated English clockmaker, then invented the marine chronometer, a key piece in solving the problem of accurately establishing longitude at sea, thus revolutionizing and extending the possibility of safe long-distance sea travel. Though the British rewarded John Harrison for his marine chronometer in 1773, chronometers remained very expensive and the lunar distance method continued to be used for decades. Finally, the combination of the availability of marine chronometers and wireless telegraph time signals put an end to the use of lunars in the 20th century. Unlike latitude, which has the equator as a natural starting position, there is no natural starting position for longitude. Therefore, a reference meridian had to be chosen. It was a popular practice to use a nation's capital as the starting point, but other locations were also used. While British cartographers had long used the Greenwich Meridian in London, other references were used elsewhere, including El Hierro, Rome, Copenhagen, Jerusalem, St. Petersburg, Pisa, Paris, Philadelphia, Pennsylvania, and Washington, D.C. In 1884 the International Meridian Conference adopted the Greenwich Meridian as the universal prime meridian or zero point of longitude. Noting and calculating longitude, longitude is given as an angular measurement ranging from 0 a degree at the prime meridian to plus 180 a degree eastward and to 180 a degree westward. The Greek letter I is used to denote the location of a place on Earth east or west of the prime meridian. Each degree of longitude is subdivided into 60 minutes, each of which is divided into 60 seconds. A longitude is thus specified in sexagesimal notation as 23 a degree a 27 a euro squared a 30 a euro cubed e. For higher precision, the seconds are specified with a decimal fraction. An alternative representation uses degrees and minutes, where parts of a minute are expressed in decimal notation with a fraction, thus, 23 a degree a 27.500 a euro squared e. Degrees may also be expressed as a decimal fraction, 23.45833 a degree e. For calculations, the angular measure may be converted to radians, so longitude may also be expressed in this manner as a signed fraction of I euro, or an unsigned fraction of 2 I euro. For calculations, the west-east suffix is replaced by a negative sign in the Western Hemisphere. Confusingly, the convention of negative for east is also sometimes seen. The preferred conventional euro that east be positive a euro is consistent with the right-handed Cartesian coordinate system, with the North Pole up. A specific longitude may then be combined with a specific latitude to give a precise position on the Earth's surface. Longitude at a point may be determined by calculating the time difference between that at its location and coordinated universal time. Since there are 24 hours in a day and 360 degrees in a circle, the Sun moves across the sky at a rate of 15 degrees per hour. So if the time zone a person is in is 3 hours ahead of UTC, then that person is near 45 a degree longitude. The word near was used because the point might not be at the center of the time zone. Also, the time zones are defined politically, so their centers and boundaries often do not lie on meridians at multiples of 15 a degree. In order to perform this calculation, however, a person needs to have a chronometer set to UTC and needs to determine local time by solar or astronomical observation. The details are more complex than described here. See the articles on universal time and on the equation of time for more details. Singularity and discontinuity of longitude. Note that the longitude is singular at the poles and calculations that are sufficiently accurate for other positions, may be inaccurate at or near the poles. Also, the discontinuity at the a plus or minus 180 a degree meridian must be handled with care in calculations. An example is a calculation of east displacement by subtracting two longitudes, which gives the wrong answer if the two positions are on either side of this meridian. To avoid these complexities, consider replacing latitude and longitude with another horizontal position representation in calculation. Plate movement and longitude. The Earth's tectonic plates move relative to one another in different directions at speeds on the order of 50 to 100 mm per year. So points on the Earth's surface on different plates are always in motion relative to one another. For example, the longitudinal difference between a point on the equator in Uganda, on the African plate, and a point on the equator in Ecuador, on the South American plate, is increasing by about 0.0014 arcseconds per year. These tectonic movements likewise affect latitude. If a global reference frame such as WGS-84 is used, the longitude of a place on the surface will change from year to year. To minimize this change, when dealing just with points on a single plate, a different reference frame can be used, whose coordinates are fixed to a particular plate, such as 83 Namibian dollars for North America or ETRS 89 for Europe. Length of a degree of longitude. The length of a degree of longitude depends only on the radius of a circle of latitude. For a sphere of radius A, that radius at latitude I is times A, and the length of a 1-degree arc along a circle of latitude is. When the Earth is modeled by an ellipsoid, this arc length becomes, where E, the eccentricity of the ellipsoid, is related to the major and minor axis by. An alternative formula is, where A, cos I decreases from 1 at the equator to 0 at the poles, so the length of a degree of longitude decreases likewise. This contrasts with a small increase in the length of a degree of latitude, equator to pole. The table shows both for the WGS-84 ellipsoid with A equals 6,378,137.0 am and B equals 6,356,752.3142 am. Note that the distance between 2 points 1 degree apart on the same circle of latitude, measured along that circle of latitude, is slightly more than the shortest distance between those points. The difference is less than 0.6 am. Ecliptic latitude and longitude. Ecliptic latitude and longitude are defined for the planets, stars, and other celestial bodies in a broadly similar way to that in which terrestrial latitude and longitude are defined, but there is a special difference. The plane of zero latitude for celestial objects is the plane of the ecliptic. This plane is not parallel to the plane of the celestial equator, but rather is inclined to it by the obliquity of the ecliptic, which currently has a value of about 23°26 euro squared. The closest celestial counterpart to terrestrial latitude is declination, and the closest celestial counterpart to terrestrial longitude is right ascension. These celestial coordinates bear the same relationship to the celestial equator as terrestrial latitude and longitude do to the terrestrial equator, and they are also more frequently used in astronomy than celestial longitude and latitude. The polar axis is perpendicular to the plane of the equator, and parallel to the terrestrial polar axis. But the pole of the ecliptic, relevant to the definition of ecliptic latitude, is the normal to the ecliptic plane nearest to the direction of the celestial north pole of the equator, that is 23°26 euro squared away from it. Ecliptic latitude is measured from 0 degree to 90 degree north or south of the ecliptic. Ecliptic longitude is measured from 0 degree to 360 degree eastward, along the ecliptic from the vernal equinox. The equinox at a specific date and time is a fixed equinox, such as that in the J2000 reference frame. However, the equinox moves because it is the intersection of two planes, both of which move. The ecliptic is relatively stationary, wobbling within a 4-degree diameter circle relative to the fixed stars over millions of years under the gravitational influence of the other planets. The greatest movement is a relatively rapid gyration of Earth's equatorial plane whose pole traces a 47-degree diameter circle caused by the Moon. This causes the equinox to precess westward along the ecliptic about 50 euro³ per year. This moving equinox is called the equinox of date. Ecliptic longitude relative to a moving equinox is used whenever the positions of the Sun, Moon, planets, or stars at dates other than that of a fixed equinox is important, as in calendars, astrology, or celestial mechanics. The era of the Julian or Gregorian calendar is always relative to a moving equinox. The years, months, and days of the Chinese calendar all depend on the ecliptic longitudes of date of the Sun and Moon. The 30-degree zodiacal segments used in astrology are also relative to a moving equinox. Celestial mechanics uses both a fixed and moving equinox. Sometimes in the study of Milankovitch cycles, the invariable plane of the solar system is substituted for the moving ecliptic. Longitude may be denominated from 0 to radians in either case. Longitude on bodies other than Earth. Planetary coordinate systems are defined relative to their mean axis of rotation and various definitions of longitude depending on the body. The longitude systems of most of those bodies with observable rigid surfaces have been defined by references to a surface feature such as a crater. The North Pole is that pole of rotation that lies on the north side of the invariable plane of the Solar System. The location of the Prime Meridian as well as the position of bodies' North Pole on the celestial sphere may vary with time due to precession of the axis of rotation of the planet. If the position angle of the body's prime meridian increases with time, the body has a direct rotation. Otherwise the rotation is said to be retrograde. In the absence of other information, the axis of rotation is assumed to be normal to the mean orbital plane. Mercury and most of the satellites are in this category. For many of the satellites, it is assumed that the rotation rate is equal to the mean orbital period. In the case of the giant planets, since their surface features are constantly changing and moving at various rates, the rotation of their magnetic fields is used as a reference instead. In the case of the Sun, even this criterion fails, and an agreed-upon value for the rotation of its equator is used instead. For planetographic longitude, west longitudes are used when the rotation is prograde, and east longitudes when the rotation is retrograde. In simpler terms, imagine a distant, non-orbiting observer viewing a planet as it rotates. Also suppose that this observer is within the plane of the planet's equator. A point on the equator that passes directly in front of this observer later in time has a higher planetographic longitude than a point that did so earlier in time. However, planetocentric longitude is always measured positively to the east, regardless of which way the planet rotates. East is defined as the counterclockwise direction around the planet, as seen from above its north pole, and the north pole is whichever pole more closely aligns with the Earth's north pole. Longitudes traditionally have been written using E, or W instead of plus or A to indicate this polarity. For example, the following all mean the same thing: a 91 a degree, 91 a degree W, plus 269 a degree, 269 a degree E. The reference surfaces for some planets are ellipsoids of revolution for which the equatorial radius is larger than the polar radius. In other words, they are oblate spheroids. Smaller bodies tend to be better approximated by triaxial ellipsoids. However, triaxial ellipsoids would render many computations more complicated, especially those related to map projections. Many projections would lose their elegant and popular properties. For this reason, spherical reference surfaces are frequently used in mapping programs. The modern standard for maps of Mars is to use planetocentric coordinates. The Meridian of Mars is located at Aereo crater. Tidally locked bodies have a natural reference longitude passing through the point nearest to their parent body, 0 a degree the center of the primary facing hemisphere, 90 a degree the center of the leading hemisphere, 180 a degree the center of the anti-primary hemisphere, and 270 a degree the center of the trailing hemisphere. However, libration due to non-circular orbits or axial tilts causes this point to move around any fixed points on the celestial body like an analemma. See also: References. External links, resources for determining your latitude and longitude, IAU-IAG Working Group on Cartographic Coordinates and Rotational Elements of the Planets and Satellites, Longitude Forged, an essay exposing a hoax solution to the problem of calculating longitude, undetected in Davis Sobel's longitude, from TLS, November 12, 2008. Board of Longitude Collection, Cambridge Digital Library, complete digital version of the board's archive, longitude and latitude of points of interest, length of a degree of latitude and longitude calculator.